Let us see what is meant by static timing analysis. Static timing analysis is a method of validating the timing performance of a design by checking all possible paths for timing violations by not simulating the design. All synthesized designs are broken down into timing paths. Each timing path has a start point and an end point. Now let us try to understand what is meant by the starting point and what is this ending point. So if you see here, there are only two types of start points in the design. First one is input port of a design and second one is clock pin of a sequential cell. So if you see this particular diagram, here this point is called as starting point. So this is nothing but an input port of a design. So next one is clock pin of a sequential cell. So if you see here, this is also one of the input point, that is clock pin of a sequential cell. You can see this one, this flip-flop comes under sequential. Now let us see what are the endpoints. Here data input pin of a sequential cell and one more thing is output port of a design. So again coming to the same figure, now let us see what are the endpoints. So endpoints is data input pin of a sequential cell. So here if you see, this point is called as data input pin of a sequential cell and this is called as an output port of an design. So simply if you see here, this is path 1, this is path 2, this is path 3 and this is path 4. So if you see the path 1, it contains one starting point and one ending point. So if you see here, this is called as start point, this is called as end point. So in path number 1, starting point is data 1 and ending point is data input pin of a sequential cell. And coming to path 2, here this is called as start point and this is called as an end point. Similarly, coming to path number 3, this is called as start point and this is called as an end point. Next, coming to path number 4, this is called as starting point and this is called as an ending point. Now we want end points, right? So here data input pin of an sequential cell. So here this is called as data input pin of an sequential cell, or else you can take this one also. This is called as an data input pin of an sequential cell, comes under end point. And one more thing is the output port of a design. So check the end points. So here this is the end point which is called as output port and here also the same thing. So finally we understood what are starting points and ending points. So simply remember these four path number 1, 2, 3 and 4 and better try to write like what is starting point and what is ending point. Then you will try to understand easily like what is meant by the starting point and an ending point. Now coming to the next point, there are two types of timing arc. One is cell delay, another one is net delay. Cell delay timing arc are defined by the type of the cell delay model used in the technology library. And coming to the net delay timing arcs are defined by the operating conditions which specify the type of resistance capacitance tree model to use. Simply you can treat a particular cell. So a propagation delay you can consider. The time taken by the input to propagate to the output is called as a propagation delay. So let us see one of the example. So if you take an inverter, it will have one input and one output. So here cell delay means it will be because of this particular cell. That is called as a cell delay, whereas net delay is because of these wires. So here this is called as a net, or else you can call it as wire. Similarly, you can call here this as net or else wire. So the delay that you are getting because of this wire is called as wire delay or net delay, and the delay that you are getting because of this cell is called as an cell delay. So the cell delay will be present in the .lib. So if you have not watched the previous videos, please try to go through those videos first so that you will be understanding the parameters like what is meant by cell rise, cell fall, rise transition and fall transition. So once if you understand this one, then you will get to know like what is meant by cell delay, and in the upcoming videos we will try to understand what is meant by the wire delay or else net delay. So mainly in static timing analysis, the design will be segregated into parts. So mostly these four parts will be there. So path number 1 is called as an input to register. So here this is called as an input and here this is called as an flip-flop, right? So flip-flop is also called as an register. So here this is one path coming from input to register. Next one, path number 2, this is coming from register to register. So this is one register and this is another register. So that's why from here to here it is called as register to register timing path. Now coming to the third one. So here this is register and this is output. So here path number 3 is from register to output. And coming to fourth one, this is called as input. This is called as an output. So that's why we are calling this as input to output. So complete static timing analysis, you'll be seeing these 4 timing parts. One is input to register, next one is register to register, register to output, and input to output. So better be clear with these 4 timing parts and try to understand what is meant by start point and end point. So depending upon the path, you try to write what is meant by start point and end point till you get clarity on what is meant by start point and end point. So once if you practice like this, you'll become familiar so that in the upcoming videos, you'll be understanding very easily. Now let us see what is meant by static timing analysis and dynamic timing analysis. Here STA stands for static timing analysis, DTA stands for dynamic timing analysis. So let us see the comparison between these two. So coming to STA, it does not check the functionality, whereas in case of dynamic timing analysis, it checks the functionality. It is also called as gate level simulation. Next, no input vectors are required. Here we are not applying any input vectors. So just by using .libs, static values will be used in order to calculate the delay, whereas here we are applying input vectors. So that's why here this point input vectors are required. Next, it is faster since it does not involve simulations. So here much simulations won't happen. Why? Because we will be using the static values from the .lib, whereas here it is slower since it consumes simulation cycle. Here simulations will be happening depending upon the test cases that we apply, or else you can call it as stimulus or else test bench, anything is same. Suitable for the complex designs. This is not suitable for the complex designs. Only simply understand the difference between STA and DTA. Here in static timing analysis, we'll be taking the delay values from the .lib, whereas in case of dynamic timing analysis, we'll be applying stimulus and we will be calculating delay as well as we'll be checking the functionality also. But here the problem is it is more time consuming. Why? Because let us see an example. If you take a 2 input AND gate, it contains 2 inputs are A and B and output is Y. So here as 2 inputs are there, you will be getting 2 power 2 combinations, that is 4, which is 0 0 0 1 1 0 and 1 1. Like this, suppose if you are having a design which contains suppose 100 inputs, then 2 power 100 combinations are needed. So this many number of test vectors we need to apply and we need to check the functionality, so that it will be more time consuming and it requires more simulation time. So that's why static timing analysis is faster compared to dynamic timing analysis. So this is the main difference between STA and DTA.